Welcome to a brief discussion of aromaticity, antiaromaticity, and Huckel's rule. I'm going to start by paraphrasing Huckel's rule, which states that conjugated cyclic organic species with 4n plus 2 pi electrons exhibit an unusual stability and tendency to be planar. Examples of these kind of species would be things like cyclopentadienyl anion or the benzene molecule. Conversely, conjugated cyclic organic species with 4n pi electrons tend to exhibit an unusual instability and tendency to contort and twist in any way they can so that they are not planar. And some classic examples of this are cyclopentadienyl cation and 1,3-cyclobutadiene. So what we're going to do today is take a look at some molecular orbital theory which will help us explain this unusual observation and this pattern of stability and instability as we add 2 pi electrons to each system. So let's get started with that now. Okay, so let's begin our exploration of Huckel's rule and aromaticity by considering the two simplest cyclic conjugated alkenes that we can draw. This would be 1,3-cyclobutadiene and benzene. Now you'll notice that in this depiction I've shown 1,3-cyclobutadiene as having 2 isolated pi bonds, but I've drawn the benzene as having 3 delocalized pi bonds which are spread out over the entire ring, meaning that each carbon-carbon bond is really more like a 1.5 bond than a double bond. Now that's not an accident, and to show why I've done this, I'm going to draw the frost circles for 1,3-cyclobutadiene and benzene. And let's start with benzene. To produce the frost circle, of course, I first draw my circle, and then I inscribe inside of that circle a polygon with a number of sides equal to that of the ring. So 6 atoms means 6-sided polygon. And we always inscribe point down. Now when I do this, the corners of my polygon represent energies of the molecular orbitals in the pi system for that molecule. And a horizontal line bisecting the circle gives me the non-bonding energy. So any molecular orbital below this line would be considered a bonding molecular orbital, whereas any orbital above this line would be an antibonding molecular orbital. And if an orbital should fall directly on the line, we call that a non-bonding. So if I take the 6 pi electrons from benzene and populate this frost circle diagram, what I notice immediately is that all 6 pi electrons have made their way into bonding molecular orbitals, which means there's an energetic benefit to having this pi system conjugated. For this reason, benzene will lay flat and align all the p orbitals of its atoms within the ring so that these electrons can have free run of the entire ring, thereby creating this aromatic situation. Now, if instead I draw a frost circle for 1,3-cyclobutadiene, we should immediately notice that we're dealing with some higher energy molecular orbitals here. Specifically, we now have 2 non-bonding molecular orbitals. And when we populate this system with the pi electrons from the 1,3-cyclobutadiene, what we're going to discover is that 2 of those electrons go into non-bonding molecular orbitals. Now these electrons would much rather be in an isolated pi bond where they can be of lower energy. And so with 1,3-cyclobutadiene, that's exactly what we see. We see a molecule which has 2 carbon-carbon double bonds and 2 carbon-carbon single bonds, rather than a molecule in which these pi bonds have been spread out all the way around the ring evenly. When this happens, we call the molecule antiaromatic, because it has no desire to let those electrons run freely around the ring. And in cases where it's possible, the molecules may even twist and contort in an attempt to misalign the p atomic orbitals to prevent this from happening. And we'll take a look at that in a little bit more detail later. Okay, so now that we have a good working definition of aromatic and antiaromatic, let's take a look at a few more cyclic conjugated alkenes and see if we can spot the trend that is Huckel's rule. Here I've shown 1,3,5-cyclobutadiene, benzene, 1357 cyclooctatetraene and 13579 cyclodecapentaene. Now the frost circle for 1,3-cyclobutadiene predicts that those 4 electrons in the pi system would have to move, at least 2 of them, into non-bonding molecular orbitals in order to create a conjugated system. And so 1,3-cyclobutadiene is an antiaromatic compound, and its pi electrons will stay in isolated pi bonds. Benzene, on the other hand, has a frost circle which allows us to predict that when we populate it with the 6 pi electrons from benzene, that all of those electrons go into bonding molecular orbitals. Therefore, benzene has a great deal of stability when it is flat. And benzene will be aromatic, giving those pi electrons free run of the entire ring. Cyclooctatetraene creates a frost circle something like the cyclobutadiene did. Notice that there are non-bonding molecular orbitals in the pi system, and that when we populate that frost circle with the 8 pi electrons from the octatetraene, that 2 of those electrons go into non-bonding molecular orbitals. So again, cyclooctatetraene will be antiaromatic, and in fact will have isolated pi bonds. We even see in cyclooctatetraene a pucker, so that the molecule deforms out of a planar configuration, specifically to avoid becoming aromatic. Now the cyclodecapentaene molecule, on the other hand, creates a frost circle which looks a little bit more like benzene, where there are sufficient bonding MOs to hold all 10 of the pi electrons. So in this case, we expect those pi electrons will have a free run of the ring, meaning that it is an aromatic compound. So now we should start to notice the trend. The trend is that 4 pi electrons and 8 pi electrons lead to antiaromatic compounds, while 6 pi electrons and 10 pi electrons have led us to aromatic compounds. And Huckel's rule is a general statement of this trend, that 4n pi electrons leads to antiaromaticity, while 4n plus 2 pi electrons leads to aromaticity. So now we've succeeded in defining aromaticity and antiaromaticity and on observing Huckel's rule. So that's all for now. I'll see you next time. Thanks for watching.